Thank you, Jen. Dr. Mason, colleagues, students, distinguished guests, it's my pleasure to welcome all of you on behalf of City University of Hong Kong. We're delighted to have Dr. Thomas Mason here to talk about science and technology for the energy challenge. As I think you're all aware, the energy issue is one that affects everyone on the planet. In fact, we could describe having adequate energy for everyone as a kind of grand challenge to civilization. At CityU, to give some local perspective, we're engaged with and in providing leadership for the energy challenge at CityU. About 5 years ago, we launched a School of Energy and Environment, the first of its kind in Hong Kong. And of course, we have many colleagues and students working across the campus in many fields, working in energy-related projects, because energy is intrinsically very interdisciplinary. We also recognize that City University is a small city with about 30,000 individuals who work and study here. And we're dedicated to promoting sustainability and energy savings in our community and regionally. We're working hard at CityU to reduce our carbon footprint and encouraging everyone connected with CityU to participate in the greening of our campus. I also want to mention that next month, October 22nd and 23rd, CityU will be hosting a sustainability summit as part of our 30th anniversary celebration. And the summit will bring together local and international experts to reflect on major issues that in many respects are related to the energy challenge. We hope all of you will participate in the summit. As an international leader in energy science and technology and director of one of the world's leading energy research laboratories, Dr. Mason has much to contribute to our thinking about the energy challenge. We're delighted to have him here with us today, and we look forward to hearing his perspectives. So please join me in welcoming Dr. Mason.
Okay, well, thank you for giving me the opportunity to talk to you a little bit about some of my thoughts on the challenges facing us and maybe some of the solutions. In a way, I'm glad that President Kuo is not here because he's written a book on this topic, so it would maybe a little bit presumptuous to come and lecture him about the content of his own book. But since he's not here, I can lecture you about some of the things that maybe he's written about. So I wanted to start by just sort of stepping back for a little bit and invoking some of the remarks that were made by one of my predecessors, Alvin Weinberg, who was the director of Oak Ridge National Lab for many years, from the early 50s until the mid-70s. And he, in addition to building up the institution as it is now, he was also a very deep thinker about how to prioritize your efforts in R&D, and what are the really important problems to work on. And he also coined the phrase big science, which is now used to describe some of the things we do with large facilities, working in large teams, trying to tackle some of these important problems. And in a book called Reflections on Big Science, which was published in the late 60s, which was sort of a collection of his essays, he talked about what he called the Malthusian dilemmas and their relationship to the laws of thermodynamics. Now, most of you have probably heard at some point in time during your education about the Malthusian catastrophe. This was the prediction around the turn of the last century, just a little bit before 1900, that if you looked at the growth of global population and the growth in food supply, those two lines crossed fairly closely after 1900. In other words, the number of people in the world was going to outstrip the food supply. And so Malthus, recognized this was probably a problem, and in fact said, if we don't do something, we're going to have, global conflict over food supply, starvation, terrible catastrophes will befall because of this outstripping of population growth with food supply. Now, it turned out that didn't happen. And it really wasn't because his projections were wrong in terms of population growth. The population growth more or less did what was expected. The reason there was no catastrophe is because the rate of growth in food supply changed dramatically. And the main reason it changed dramatically is because of scientific innovation. In particular, the fixing of nitrogen that was discovered by a chemist working in Germany, Fritz Haber, and the fact that that then allowed you to produce fertilizer at industrial scale. And that was a fundamental shift in the productivity of agriculture that allowed the world to avoid the Malthusian catastrophe. So the modern day versions, and there's two of them that Weinberg talks about, and actually we're confronting both of them to varying degrees today, of the Malthusian catastrophes, is probably not related to food supply, because actually we're still in a world where we can produce enough food, and projections would suggest we can continue to do that. Where we see starvation, it's because of problems in distribution, not because of overall food production. But there are other constraints on the system that could become significant, and they relate to the laws of thermodynamics in the sense that one of them relates to conservation of energy and the other one has to do with entropy. So the conservation of energy one is really resource depletion and scarcity. Is the growth in population with the energy demand that goes with that, combined with the rising energy consumption per capita as the developing world approaches higher standards of living, going to outstrip the finite resources on the earth. And it's, of course, not just energy, but energy is certainly one of the problems. Now, just as with the original Malthusian prediction, there was essentially a technological fix in the form of fertilizer and improving agricultural productions. Of course, there are technological fixes in the form of energy technologies that may help in terms of at least the supply, although there are environmental consequences associated with that supply that you have to be concerned about, in addition to just where do you get the energy from. And in addition, it turns out that if you have sufficient energy, you can probably overcome most of the other resource depletions. And the reason for this is that if you look at the kind of critical materials that we use to produce the world around us, although we might run out of some particular higher grade ore, you can always go to lower grade ores if you've got a lot of energy. So for example, aluminum we get from bauxite. And maybe someday we'll run out of bauxite, but then we can go to kaolite clays and the aluminum concentration isn't as high, but as long as you've got the energy, you can get to it. And it turns out if you look at the resources that are aluminum, steel, copper, all the things that we use to manufacture our world, almost all of them have alternatives that can be used, that really the principal cost is associated with the energy content in the production. So we're really not likely to run out of atoms as long as we have enough energy to get those atoms into the form we want them. So in terms of scarcity, I think you can take the general problem of scarcity and turn it into an energy question. And then that's the question I'm going to spend most of the time talking about. There's actually another dilemma that can come about that's not associated with energy, but associated with entropy. And of course, we know that entropy increases as a function of time, generally speaking. And the way to think about this is the growth in complexity, and that's also a consequence of population growth. So just as our consumption is increasing consumption is a consequence of population growth, as the population grows, the complexity also grows, and it grows faster than linear in population, because in the end, complexity in human society is all about the interactions between people. So it's not just the number of people, but how many possible interactions can they have. And of course, that automatically gives you something that grows more rapidly than linear. The question then is, how can you manage very large societies with large numbers of people? And of course, the technological fix there, if you will, that potentially could avoid getting into very chaotic situations just because of the complexity and the interactions between people. A lot of it revolves around our information technology and our ability to manage information. So, things like high-performance computing, high-speed networks, and so forth, while they increase complexity, they also offer us tools to manage complexity. And I'm not going to spend a lot of time talking about this one. That would be like a whole nother talk. It's actually a very interesting topic. It brings in all kinds of challenges in terms of privacy and so forth. But it's another area that I think it's important to be thinking about, is how can we use those tools to help us manage the complexity that goes with growing populations. So for the rest of the talk, I'm really going to focus on this first one. And as I said, I'm going to treat it as if scarcity in raw materials is really an energy problem based on the arguments that Weinberg made in the 70s, which actually we've re-looked at recently. I had a master's student who was looking at some of these things in terms of the supply of raw materials, and actually, remarkably, the argument still holds 40 years later. If you look, even though there's been tremendous growth in demand, actually a lot of it driven by China, for raw materials, generally speaking, the supply has kept pace because there's been, prices go up, therefore there's an aggressive push to get more supply, and it may be harder to get to and take more energy to get at it, but in the end, the total estimated reserves for most of the critical commodities have been roughly constant since the 70s when Weinberg did this analysis. So I think it's certainly